In these problems, we're going to go over some convergence and divergence of series questions. The tests we're going to use are essentially the comparison test, both a direct comparison and a limit comparison. Sometimes the integral test, we may make reference to a few other things here, but mostly focused on comparison test and integral test here. So first series we're going to look at, we're doing summation n equals 1 to infinity, 1 over n times the square root n squared plus 1. Okay, this one, you could try and do an integral of 1 over x times square root x squared plus 1. I'm guessing that's going to get fairly difficult here. As a comparison, this is going to be, I think, a lot simpler here. So essentially here, my thought process here is, first of all, and before we start doing this, is that if I do a series n equals 1 to infinity, 1 over n to the p, this is called a p series here. And this particular series it'll converge here if p is greater than 1, and it'll diverge if 0 less than equal to p less than equal to 1. So basically p less than equal to 1. So 1 is our dividing point, 1 over n to the p. These are called p series. So typically here, you could do an integral test, I guess, to check that there. Just integrate 1 over n to the p from 1 to infinity with respect to n, I guess. This falls out pretty easily. Now, what I'm going to do here then is I want to think of 1 over n times square root of n squared plus 1 kind of like a p series. So 1 over n times square root n squared plus 1, I want to think of that as like 1 over n to the p, or at least more or less that. So what I look at here is that as n gets big, this n squared plus 1 is going to be essentially n squared. If n is a million squared plus 1 is essentially just a million squared. So what I think in my head is this is 1 over n times square root of n squared. Square root of n squared is just n. So essentially, I get 1 over n squared. So this 1 over n times square root n squared plus 1, in my head I think, oh, that's like 1 over n squared. And then I think about my p series. Well, that'd be a p equals 2. And this tells me I expect this series to converge. Now, in some sense, once you get comfortable with this, that might be enough to convince yourself this converges. But to show this, here we can do a comparison test. So I'm going to do this in a couple ways. One is a direct comparison test. Here. So it's a comparison test, but it's direct. If people just say comparison test, probably they're talking about the direct comparison test here. And the idea here is you want to find a series. Now, if we want to show our original series converges, what we want to do is find a series so that n equals 1 to infinity, say an converges here, but we have an to be, let's see, we want an's to be bigger than 1 over n times square root n squared plus 1. And you just actually need this for all n that gets sufficiently big, so all n greater than 100 or greater than 2 or greater than just something here. Now, in this case, to do that, I'm going to hope that this will be 1 over n squared will work as my an. What I tend to do is start on the right-hand side here. Start with 1 over n times square root n squared plus 1. And because I want to show that this converges, I need to make this bigger here. So the idea here is that if the sum of the an's converge, and the thing we're looking for, summing those up, is less than the sum of the an's, because each term is less, well then this sum of these things we're looking for that series has to also be convergent, because it's sort of going to be finite, because it's less than a finite number. We're assuming here also that nothing is negative. I guess everything's non-negative, or perhaps even positive. All right, so I'm going to make this bigger. How do I make a fraction bigger? Well, I make the denominator smaller or the numerator bigger. So I'm going to look at the denominator smaller. And so if I just drop that plus 1, that makes my denominator smaller, which makes the whole fraction bigger. And then for positive n's, this is 1 over n times n, which is 1 over n squared. So what we're going to use is our an is 1 over n squared. And what we get here now is 1 over n times square root n squared plus 1 is less than equal to 1 over n squared. So let's maybe put this together. Whoops, sorry. Let's put this together in sort of a final form here. So what we get is 1 over n times n squared plus 1 less than 1 over n squared. And if I do n equals 1 to infinity, 1 over n squared, this converges because this is a p-series. So once you get those two, so that tells us that the series n equals 1 to infinity, 1 over n times square root n squared plus 1 also converges. And that's really what we wanted to show here. Or we want to determine whether that series converged or diverged. Note, this series will converge to less than whatever the sum of the ANs converge to here, because we're sort of correct, or sort of have this inequality for all n here, or all positive n. If you wanted to show that a series diverged, everything works the same, except you have to show that your ANs are less than equal to the sequence inside of the series you're trying to show diverges. That is bigger than infinity. Series. I can't really do that here because that's not going to work. So let's direct comparison test, and that's kind of the standard thing to do here. But there's another one. That's the limit comparison test here. And what this does here is I take a limit as n goes to infinity. And what I'm going to get here is I'm going to do 1 over n times square root n squared plus 1 over sort of the sequence I think is essentially equivalent to 1 over n times square root n squared plus 1 here. So I'm going to take this limit. I'm going to call this L here eventually. So we'll say maybe L equals that. So I'm going to find this limit. And we'll do a limit as n goes to infinity. I can sort of take the reciprocal of the bottom. I get n squared over n times square root n squared plus 1. And let's see. I can cancel an n here. So I get n over square root n squared plus 1. And then you could multiply top and bottom by 1 over n. Really by square root 1 over n squared on the bottom's case. And that gives you a limit as n goes to infinity of 1 over square root 1 plus 1 over n squared. And then that 1 over n squared goes to 0. This is going to give us a 1 over square root of 1, which is 1. Okay, for the limit comparison test, we take this limit, we take the sequence sort of definition here, function, sequence function, for the series we're concerned about, and then we take a ratio of that with sort of some other sequence where we happen to know whether this associated series to that sequence, like this guy here, converges or diverges. Okay, and then we got 0 less than L less than infinity. This is like the limit comparison test for improper integrals. And that tells us that these two series, n equals 1 to infinity, 1 over n squared, and this series n equals 1 to infinity, 1 over n times square root n squared plus 1, either both converge or they'll both diverge. So essentially what you're saying is that as n gets really big, these terms inside are essentially the same here. And that means that when you add up an infinite number of them, you're either going to go to infinity for both or to some finite number for both. And it's essentially the same finite number for both, but it'll be a little bit of discrepancy because they're not actually the same, a little different. They're a little different here. Okay, and in our case here, we know that the first series converges. So we get n equals 1 to infinity, 1 over n squared is a p-series. So this converges. So the series we actually care about also converges. So the series we care about converges. So you can do this problem either as a direct comparison or a limit comparison. Okay, next one here. This one we have a summation n equals 1 to infinity, 1 over n squared minus 1 over n cubed. Okay, so to use these comparison test methods, first thing we really want to have here is that our terms are positive. Note 1 over n squared is bigger than 1 over n cubed. N cubed is bigger than n squared, so the n cubes have a bigger denominator. And I'm taking bigger denominator gives you a smaller number. So I'm taking bigger number minus smaller number. That's going to give me a positive here. And so what I want to do here is I want to first determine, do I think this converges or not? The answer is really yes here. So what I'm going to do is I think this is going to converge, and I'm going to do a direct comparison. So what I want to do is I want to bound this above 1 over n squared minus 1 over n cubed by something that I know will converge. So how do I make this bigger? Well, we can just not subtract the 1 over n cubed. So you could bound that above by 1 over n squared. And here I just sort of wrote that down, but it should be sort of obvious. And if you do n equals 1 to infinity 1 over n squared, that series converges here. So what we get is that the series n equals 1 to infinity 1 over n squared minus 1 over n cubed converges. So this is by the direct comparison test here, or just the standard comparison test. So that's really pretty quick and easy here if you recognize how to do this. You sort of mix two terms here. There's other ways to do this here. For instance, another thing you could do is say that the series n equals 1 to infinity 1 over n squared minus 1 over n cubed, if both of these sort of series I'm going to write down converge, we can get the following equation: n equals 1 to infinity 1 over n squared, that series, minus the series n equals 1 to infinity 1 over n cubed. So this equal sign only works if both of these converge, but they're both p series, so they will both converge here. And so you'll get here that this equals, well, this is convergent here. And so we can say that really our series n equals 1 to infinity 1 over n squared minus 1 over n cubed is the difference of two convergent series. And now I'm trying to think about that. I want to say this, but I'm not in. Yeah, that should work. So it should be, this will work out. Should be the difference of two convergent series. So that's really our original series is convergent. Now this is kind of a higher level feeling way to do this, but really not that hard either. So that's just sort of another way to do this problem here. You could also, I guess, have done an integral test here. Would have been, would have worked out, but these comparisons work pretty slick. Next one here. Back to black writing here. We've got a series here. We're doing n equals 2 to infinity 1 over n times natural log n squared. Okay, so this one, what I might be trying to do here, see 1 over n times natural log n squared. What I'm sort of better 2 there. What I'm thinking about here is if this was just 1 over n inside, this would diverge. But I multiplied by some more stuff, so there's some hope that this converges here. Just is this other stuff big enough on the bottom, so that natural log n squared, to make our denominators bigger, to make our terms small enough for this to converge? Well, okay, let's see. We've got natural log n here, squared. What I'd like to do if this is going to converge is bound this above. So how do I make this bigger? I make the denominator smaller. But the thing is, that sort of obvious thing to approach this with is to get rid of the natural log n squareds. But if I do that, I get 1 over n here. So I could do that. Natural log n for n bigger than 3, say, is going to be, natural log n will be bigger than 1. So getting rid of that, this will make my denominator smaller, make the whole fraction bigger. But this does not work here. Because essentially then, what we get is that the series n equals, well, we're doing 2 to infinity now, 1 over n, this diverges here, and you have a less than equal to. So essentially what you're saying is that this original series is less than equal to infinity. Well, that doesn't really tell us anything at all. Of course it's less than equal to infinity, because sort of everything is. Okay. So we've got that figured out. Or really not figured out. So we want to do something else. So in this case, really what I would do, this looks like a nice case for an integral test. So not a comparison at all. I'm going to try an integral test. Get a better colon there. And what that means is I'm going to do an integral from 2 to infinity 1 over x times natural log x squared dx. So you could do this here. And what you get here, let's see, I'm going to let u be natural log x, and then du is 1 over x dx. And if you look at this, what you get is an integral of 1 over, so this 1 over x, that's our sort of 1 over x here, times dx, that's our du. And then the 1 over natural log x squared gives us a 1 over u squared. And then we get some bounds. We could convert 2 to natural log of 2 and infinity to infinity here. Let's just do that for the sake of, whoops, deleted my integral sign. So my original bounds were in terms of x. So when x is 2, u is natural log 2. When x is infinity, I get natural log of infinity, which is still infinity. Do my antiderivative. I have u to the negative 2. Antiderivative is negative 1 over u. I'm going to evaluate that from u equals natural log 2 to infinity. So that gives me negative 1 over infinity. Minus a negative is plus 1 over natural log 2. 1 over infinity is 0. So this is 1 over natural log 2. Now, I don't care what this value 1 over natural log 2 is, except that it's finite here. So that means that my improper integral converges, because you got a finite number. So integral 2 to infinity, 1 over x natural log x squared dx, converges. So that means our series n equals 2 to infinity, 1 over n natural log n squared converges. Sorry, I wanted to box my answer, but I didn't write the actual answer, which is, hey, this converges. Okay. So that's really probably how I would do this one. Let's try, though. Let's see what would happen if you did not a direct comparison test, which we tried before. Let's try a limit comparison test. So let's just see what would happen here. Now, I know my series converges here, so I'm going to do a limit comparison test with something that converges. So I'm going to do a limit as n goes to infinity. We have 1 over n times natural log n squared. Let's just compare this with 1 over n squared. Let's see what happens here. I want to have to do something bigger than 1 down here. I think n squared may or may not work. I suspect not here, but let's see what happens. So you get a limit, n goes to infinity. So it'll be n squared over n times natural log n squared. Can cancel some n's. And then I have n over natural log n squared. That's going to go to infinity over infinity. So I can use L'Hopital's rule. Differentiate the top over differentiate the bottom. Whoops. Limit. N goes to infinity. Derivative of n with respect to n is 1. Bottom, I'm going to get 2 times natural log n times 1 over n by the chain rule. So that's a limit as n goes to infinity. I can bring the n to the top over 2 natural log n. I get infinity over infinity again, so we're going to apply L'Hopital's rule again. I can pull the 2 out as a 1/2. Derivative of n is 1. Derivative of natural log n is 1 over n. So this is 1/2. Limit as n goes to infinity. Oh, let's see, I get an n on top. This limit goes to infinity. So we did not get a finite number. So the way we phrased the limit comparison test before does not work. But this does tell us something. So when this goes to infinity, this ratio goes to infinity, means the top sort of sequence gets way bigger than the bottom here. So what that tells us here is that the top sequence gets bigger than the bottom. And so that tells us essentially that the series n equals 2 to infinity, 1 over n times natural log n squared should be bigger than the series n equals 2 to infinity, 1 over n squared. Now, does that help here? So this is a statement we can get out of this because this went to infinity here. Well, does that help? Well, we know that the second one converges, so we know this is some finite number. We know that the series we're concerned about is bigger than a finite number. Well, that could be a finite number, or it could be infinity. So we really didn't get any information here. So this is really just inconclusive. So that didn't work. So the integral test is probably the way to go here. Next one. Whoops. Okay, so determine whether the following series converges or diverges. N equals 1 to infinity, n times log n. This problem's really easy, but it might confuse some people here. This one, we can use the nth term divergence test. Nth term divergence test, or maybe you just have this called the divergence test here. And really what this says is that the sequence inside the series does not converge to 0, so the series just cannot converge. So every other series we've had so far, the sequence inside would have went to 0 as n goes to infinity. This isn't the case here. So you just say the limit as n goes to infinity of n times natural log n. This is actually going to go to infinity times infinity is infinity. Certainly does not go to 0. And that just tells us series n equals 1 to infinity and log n diverges. Here, so simple use of this nth term divergence test. Whoops, next one. Okay, so determine whether the following series converges or diverges. Here we have natural log n over n cubed. Now, I want to come up with something that's essentially like natural log n over n cubed. Often the trick is these natural log n's are really smaller than n to the essentially any positive number at all. So n to the 0.001 will get bigger than natural log n eventually. Here, so essentially I kind of ignore the natural log n in some sense and see this as 1 over n cubed. The only time that doesn't really work is when I'm dealing with 1 over n itself. Like we had 1 over n times natural log n squared before, and that ended up converging here. But whenever you got 1 over n with the natural log n, sometimes those natural log n's push things just a little too big or a little too small here. But if you've got an n cubed, you've got some wiggle room here, and I'm going to think this is probably going to converge. Now, I can do this in a couple ways. So I can do direct convergence. Probably I can do this in several ways. So if I, sorry, not direct convergence. Direct comparison test here. And what I'm going to do here is I'm going to take natural log n over n cubed. I suspect my series converges, so I'm going to try and show something is bigger than this. So how do I make this bigger? Well, I can replace natural log n with something bigger than natural log n. Make the numerator bigger. So n will be bigger than natural log n here for n bigger than probably at least 2 or something like that. Eventually, something very small n that'll work. You could take derivatives or something to figure that out. Here, I'm not really going to get too bothered with that. Well, then this, n over n cubed, that's 1 over n squared. So natural log n over n cubed is less than or equal to n over n cubed, which equals 1 over n squared. And then my series, n equals 1 to infinity 1 over n squared. This is a p series with p equals 2. This converges. And we know that natural log n over n cubed is less than 1 over n squared. And so that tells us, so we get n equals 1 to infinity. Natural log n over n cubed converges. So we get a convergent sequence with the direct comparison test. Okay. Let's do a limit comparison, just to see how that would work. Well, here, I have to do a limit as n goes to infinity. You can put the sort of sequence you're concerned about, natural log n over n cubed, either in the top or bottom. Doesn't really matter here. I'm going to say L equals this. And then I have to compare this to some particular other series, here, or some other sequence. So the things that I think of are compare this with 1 over n squared or maybe 1 over n cubed. So let's try 1 over n cubed first. If you do 1 over n cubed, the n cubes cancel, and you get a limit as n goes to infinity, natural log n, that's going to go to infinity. Now, this is a problem, because what we have now is that this essentially tells us the top gets way bigger than the bottom. And so what that tells us is that the sum, n equals 1 to infinity, natural log n over n cubed, should be bigger than the sum, n equals 1 to infinity, 1 over n cubed. Now we know the sum, n equals 1 to infinity, 1 over n cubed, is some finite number, but we now have the series we're concerned about is bigger than some finite number. That doesn't help us, because that series we're concerned about could still go to infinity. That would be bigger than this finite number. What we want to get is that smaller. That is, if this limit was 0, That'd be good, because that'd make the denominator bigger, and we get this inequality the other way, and we'd say, oh, hey, it converges. Or, if we knew that the series n equals 1 to infinity, 1 over n cubed diverged, which is wrong, but if you had like a 1 over n here instead, you still got a limit of infinity, we could say, oh, this is infinity, essentially, and so this other series has bigger than infinity, so it's also going to go to infinity. But here, this is really inconclusive. So I have to try another L. So let's do L equals limit n goes to infinity, natural log n over n cubed over, now we're going to do 1 over n squared. So we have to make our denominator bigger. Here, how do we do that? Well, we make the denominator of the denominator smaller. We replace the n cubed with n squared. That makes the 1 over n squared bigger than 1 over n cubed here. And let's see what kind of limit we get. Limit n goes to infinity. You can flip the 1 over n squared over. You get n squared times natural log n over n cubed. You can cancel the n squared. It's on top and bottom. You get really natural log n over n. Limit as n goes to infinity. That's infinity over infinity. Use L'Hopital's rule. You get limit as n goes to infinity, 1 over n over 1. This is going to go to 0. So when you get a limit of 0, that means the bottom sequence is much, much bigger. And so what this tells us is that as n goes from 1 to infinity, natural log n over n cubed is actually smaller than the sum n equals 1 to infinity, 1 over n squared. But this series converges here. So the right-hand side here converges, the 1 over n squared series. So that's a finite number. So we know the sum n equals 1 to infinity, natural log n over n cubed is also a finite number. So we get this, and n equals 1 to infinity, 1 over n squared converges. Because really it goes to a finite number. And what those tell us is that the series we're concerned about, n equals 1 to infinity, natural log n over n cubed, that converges as well. So I think the direct comparison test is actually probably a little bit easier here, but you can use the limit comparison test as well. Next one. Determine whether the following series converges or diverges. Okay, so here's where I look at sort of what matters here. So I have the 4. That's just a constant here. Essentially, I could factor that out, and I multiply my value by 1/4. That's not going to affect convergence or divergence. 1/4 of infinity, still infinity. 1/4 of a finite number, still a finite number. Plus 1's not really going to matter. As n gets cubed, as n gets big, cube root of n is really going to dominate. And so what I see here is that this 1 over 4 times cube root n plus 1, I see this is really 1 over, now I think of it as cube root of n here. You can put the 4 here or not, really. It's not going to matter too much here. And so what I think about here, the 4 again won't affect convergence. So what I think about is, what about the sum n equals 1 to infinity, 1 over cube root of n? Well, this is sum n equals 1 to infinity, 1 over n to the 1/3. Note 1/3 is less than or equal to 1. This is a p series. And this then diverges. Here. So what I'm looking at is, essentially I suspect my original series diverges here. But we want to go show that here. So that's sort of intuitively, I'm pretty convinced that this is going to work out here, as this original series is divergent, because this is pretty much just 1 over cube root of n with some constants thrown in there that aren't going to really affect convergence or divergence. But I'm kind of hand waving like, oh, I say those don't matter. What if you don't believe me? So we want to just show this here. So in this case, we could do a comparison test. Let's do a direct comparison test first. I suspect the limit comparison test will be easier here. But let's try a direct comparison test. And it's important for a comparison test to figure out, is this going to, do we suspect that our series is going to diverge or converge beforehand? Because it tells us whether, when we write down 1 over 4 cube root of n plus 1, whether we do less than equal or greater than equal. If I'm trying to show this is divergent, I want to get something smaller over here. I'm going to do some stuff. And I kind of want to get a 1 over cube root of n, or maybe a constant multiple of cube root of n. So I want to make this smaller. How do I do that? I make the denominator bigger. Now, what we did before is we just dropped 1. If you drop the 1, that makes our denominator smaller, which makes the whole thing bigger, and our inequality does not work. So I'm going to do a trick here, a little bit different. I'm going to replace 1 with something bigger, and that bigger thing I'm going to say is cube root of n here. Now, cube root of n should be bigger than 1 for n at least 1, which is what we have here. So this should work out. I'm replacing 1 with cube root of n. That makes my denominator bigger, makes the whole fraction smaller. Seems a bit weird. I mean, it got a lot bigger. Why'd I choose cube root of n? Well, then I can take 4 cube root of n plus 1 cube root of n and get 5 cube root of n. So I really did this here, sort of direct comparison. And then when I do a series, n equals 1 to infinity, 1 over 5 cube root of n. Well, this is 5 times the series, not 5. I can pull the 5 out, but it's in the denominator, so this is 1/5 times n equals 1 to infinity, 1 over cube root of n, and that series diverges. And the 1/5 doesn't really affect things. We have infinity, multiply that by a fifth, still infinity. And so what we get here is essentially that because we have a divergent series with terms that are smaller than the series we're concerned about, what we really get is that sort of 1 over 4, sum n equals 1 to infinity, 1 over 4 times cube root of n plus 1 is greater than or equal to sum n equals 1 to infinity, 1 over 5 cube root of n, but this series on the right that we said diverges goes to infinity, so the series we're concerned about is bigger than infinity, so that has to go to infinity as well. So that diverges, that's true. That tells us that the series that we're concerned about and diverges here. Okay, so direct comparison, actually that wasn't that bad. Let's look at limit comparison. So let's do a limit comparison test. And it's going to feel kind of the same, except I'm doing a limit. So L, so limit as n goes to infinity. I'm going to do 1 over 4 times cube root of n plus 1. And I'm going to compare this, just for the sake of, just 1 over cube root of n. You could put the 4 on the bottom. It actually won't matter. When we get done, we're trying to show L is between 0 and infinity. Putting the 4 there is going to either multiply or divide L by 4 here, but if that's not going to affect whether L is between 0 and infinity or not. So what I'm going to get here is a limit as n goes to infinity. I can move my cube root of n to the top over 4 cube root of n plus 1. And you could do L'Hopital's rule here. Probably you could divide top and bottom by cube root of n. Let's maybe do that. I would personally be okay if you can just see what the limit here is. It's going to be 1/4. If you can write that down, for me that's fine, but may not be the case for every instructor you find. Cube root of n times 1 over cube root of n, that's 1. And I'll get a 4 when I distribute this 1 over cube root of n. 4 plus 1 over cube root of n. 1 over cube root of n goes to 0 as n goes to infinity. So this works out to 1/4. Again, without multiplying top and bottom by 1 over cube root of n, essentially cube root of n is going to be the dominant term on top and bottom, but you have 4 of them on the bottom, so the whole thing goes to 1/4. Now, the key thing here is that L is between 0 and infinity. So we get that the two series, n equals 1 to infinity, 1 over 4 cube root of n plus 1. And the other series, n equals 1 to infinity, 1 over cube root of n, either they both converge or they both diverge. Here. So if these both converged here, so they either both converge, both diverge, and then the idea here is you look at the simpler series here, that was the point of putting this here, 1 over cube root of n, n equals 1 to infinity. That's a p series with p less than 1, less than or equal to 1. So this second series diverges, and that tells us the first series diverges. So the series n equals 1 to infinity, 1 over cube root of n diverges. So the series we care about also diverges because they both converge or both diverge. So again, you do a limit comparison with something you know converges or diverges, and that essentially if you get the right kind of limit or you find something close enough here, gives you sort of the same convergence. And determine the convergence of the original series. Next one. Okay, this one's a little tricky here. Determine whether the following series converges or diverges. First thing I think about, well, so it's n equals 1 to infinity, sine of 1 over n. First thing I think about is, do the terms go to 0 here? Does sine 1 over n, so let's do a limit, n goes to infinity. I see that sine here, and I think this might oscillate. Here, well, sine's continuous, so I can pull the limit inside. So I get, whoops, let's pull the limit inside. I get sine of limit n goes to infinity 1 over n. Well, that's sine of 0, but that's just 0. So our terms do go to 0. So even though they're oscillating, they're getting smaller and smaller in absolute value here. So the nth term divergence test does not work here. Okay, now we want to do either a comparison or a limit comparison. I think it's going to be easier here to do a limit comparison. And we don't really know this yet. Well, let me say, I want to determine, do I think this converges, do I think this diverges? So let's maybe even do a little computer exploration here, or calculator exploration. Determine, do we think this diverges, do we think it converges? Let's see, view, there we go. So what I'm going to do here is I'm going to go to y equals, and I'm going to do sine of 1 divided by, whoops, sorry, I don't really want to put that there. I'm going to do a sum of a sequence. So I'm going to go to second list, math, do a sum of second list ops, option 5 is sequence, and I'm going to do sine of 1 divided by alpha n, close my sine, comma, n is what our variable is, and we're going from 1 up to x. So this will add the terms from n going from 1 to x here. Okay, so that should work out. I'm going to quit here. Let's just go to the table here. So the table, okay, 0 didn't work because you get 1 over 0. And I'm getting 0.84, 1.32, 1.6, 1.8, 2.26. 2.4, 2.5. These look like they just keep getting bigger and bigger, but you know, will they converge at some point? Who knows? Let's see, 3.4, 3.54, 3.58. I mean, they keep growing, but we're not really sure here. So you could look at the amount they're growing by. We're growing maybe 5.8, 0.4, 0.4, 0.37, maybe 0.36 if we go down here. Some more. Let's see, we're doing about 0.3, less than 0.3. So the amount they're growing is slower. Here the question is, do these actually converge or do they go to infinity? So I don't see them converging to anything so far. So let's maybe think about divergence here. So if I did a limit comparison and I wanted to check divergence here, probably what I want to compare this with is sort of the P series that has the sort of biggest P, that's being the closest to convergence. That's the 1 over n. So I'm going to compare to 1 over n. If I get the limit I want, I'll get that this original series diverges here. If not, I might go back and try like 1 over n squared. Check for convergence here. So I'm going to get some information either way here. So what I'm going to do, see, this is going to be a limit as n goes to infinity. Right now, if I plug in infinity, I get 1. So the top goes to 0. We did that already. Bottom also goes to 0. So I'm just going to go use L'Hopital's rule right away. I mean, typically I'd move the n to the top, but I can't sort of manipulate the sign 1 over n here. So I'm going to have to use L'Hopital's rule. So I'm going to get on top, I'll get cosine 1 over n times the derivative of 1 over n by the chain rule. That's negative 1 over n squared. On the bottom, I get the derivative of 1 over n. That's negative 1 over n squared. And a really nice thing happens here. These negative 1 over n squareds cancel. I just get the limit as n goes to infinity, cosine 1 over n. Well, as n goes to infinity, 1 over n goes to 0. So this is cosine of 0. That's just 1. Now that's a nice result for me, because this was our limit L. We got 1 here. And that tells me that essentially for really big n, sine 1 over n is about 1 over n. Here. So you might have seen this in a little different form. Somehow I feel like in a physics class, where I'll see something like sine x is roughly x for small x, or maybe sine theta is roughly theta for small theta here. Note here, this is written a little differently. As n gets big, we're really putting in smaller and smaller things. It's 1 over n. So you might have seen this somewhere else. That's essentially what we're saying is this limit is 1. Sine 1 over n and 1 over n are really close if n gets really big. And what that tells us here is we know that the sum n equals 1 to infinity, this series 1 over n, this is a harmonic series, this diverges. And we got this limit of 1. Maybe I'll write this here. And our limit is between 0 and infinity. And that means that the series n equals 1 to infinity, sine 1 over n, also diverges. We can do a nice limit comparison test here. There's ways here to do a direct comparison test as well. You can kind of show sine 1 over x maybe is bounded above, or sorry, sine 1 over n is bounded above by 1 over n, maybe using some derivatives and things like that. But I think this limit comparison test is actually a bit simpler here. Next one. Okay, so determine whether the following series converges or diverges. So we have a limit as n goes, not really a limit. We have a sum, n equals 0 to infinity, 2 to the n over 3 to the n plus 5. Now, what I'm going to see here is, first of all, as n gets bigger and bigger, 3 to the n is going to dominate here, and this is all going to go to 0. And what I've got to think about here is, how can I maybe compare this to something I know? So what I'm looking at here is n gets really, really big. 3 to the n is going to be some gigantic number, and this plus 5 isn't going to matter. So this is like 2 to the n over 3 to the n, which is like 2/3 to the n. So what I'm thinking here is that this series is basically a series of 2/3 to the n. That's if I just got rid of that plus 5, which again for really big n is going to be essentially inconsequential. 3 to the 50th is going to be some gigantic number here. The plus 5 is hardly going to matter at all. This series is geometric. That means it's sum n equals 0 to infinity r to the n here. And it's geometric with r, absolute value r, less than 1 here. And that means that this series converges. And it's actually convergent to 1 over 1 minus r. Here, that doesn't really help us here, but you might have seen this. Whoops. Wrong way there. Here, so convergent to 1 over 1 minus r. An ugly r here. That converges. You might have seen that before just to kind of remind you, but you don't really need that formula 1 over 1 minus r. You just need to know that the series converges for this question. So that's really what I'm thinking in my head is this looks geometric. I bet it converges. So what I'm going to do is I'm going to try a direct comparison. So I'm suspecting that this converges. So when I get 2n over 3n plus 5, I'm going to bound this above. And that's because I think this is going to converge. So I have to make this fraction bigger. How do I make the fraction bigger? I either make the numerator bigger or the denominator smaller. Well, I can make the denominator smaller just by dropping that 5. So it's 2n over 2 to the n over 3 to the n. That's 2/3 to the n here. And then we know that that series converges. So we get n equals 0 to infinity, 2/3 to the n converges here. And essentially the series we care about is less than that. So by direct comparison, n equals 0 to infinity, 2 to the n over 3 to the n plus 5 also converges. All right, next one here. I guess you could do limit comparison here, but I don't really like doing limits with, well, you could do it 2 to the n over 3 to the n with 2/3 to the n. You probably divide and multiply by certain things here, but I think the direct comparison works out pretty slick here. Next one. Determine whether the following series converges or diverges. We have n equals 2 to infinity. We have 1 over n times square root n squared plus n minus n. So this one throws me a little bit when I look at it. Square root, I just kind of think essentially what is this here? So what I think about this is n equals 2 to infinity. As n gets big, I have 1. I keep my n. Square root of n squared plus n. So as n gets big, n squared is going to dominate. So I'll get a square root of n squared. That's an n. Wait, that's an n minus n here. So that's going to be like 1 over n times 0 here. That seems bad. Although, actually, maybe that's good. I wonder if the limit as n goes to infinity of this sequence actually doesn't go to 0 here. In that case, this series will diverge here. Let's maybe investigate that here. Well, you could investigate that, I guess. I'm thinking that might be a little... Well, let's talk about what we do. So you could do a limit as n goes to infinity just of the series, n times square root n squared plus n minus n. I want to find that limit. Let's see. You could probably do L'Hopital's rule. When you have this difference here, one trick is to multiply by what I'm going to call the conjugate, square root n squared plus n plus n. Multiply by that top and bottom. What you get is a limit as n goes to infinity. Okay, we get a 1 over, I'm going to keep a, let's say on top, well, let's say not a 1. I'm going to get just the square root n squared plus n on top. On the bottom, I'm going to get the n. And then I'm going to get this square root n squared plus n minus n times square root n squared plus n plus n. So I'm going to use the formula a minus b. Let's write those in capitals. How about? A minus b times a plus b is a squared minus b squared. And here my a is square root n squared plus n, and my b is just n here. And so sort of using this term factor and that factor is really an a minus b times a plus b. You multiply those together, you get really n square root n squared plus n squared. That's n squared plus n minus, let's see, just n squared, that's n squared. So the two n squareds cancel. You get an n times n is n squared. So you get square root n squared plus n over n squared. And then you could, let's say, multiply top and bottom by 1 over n here, if you're not convinced what's going to happen here. When I look at this already, I see square root n squared is essentially n. So I've got essentially 2n on top, n squared on the bottom. It's a higher degree on the bottom. I suspect this is going to go to 0 here. So I could be okay with saying, oh, that goes to 0. But if you're not sure, multiply top and bottom by 1 over n. Inside the square root, that 1 over n becomes a 1 over n squared. N over n is 1. N squared over n is just n here. And this gives me a limit as n goes to infinity. So I can split up inside the square root. I get 1 plus 1 over n plus 1 over n. I get 1 plus 0 plus 1, square root of 1. So that's 2 on top over n. That's going to go to 0. All right, that's not really the result I wanted. This goes to 0 here. I was hoping this would not be 0, because if these terms did not go to 0, I'd know right away the series diverges. So I did all this work, and it's sort of wasted effort here. In some sense, if I did not get 0 here, then I'd be done. So I guess not totally wasted, but given that I got 0, this doesn't help me at all here. Maybe it lets me think about things, but directly it doesn't help. So, kind of the wrong path. Okay, so now we got to think, does this converge or diverge here? Well, what I'm thinking about here, when I look at this is 1 over n times 0. That 0 is going to make this n even smaller here. We could do a limit comparison or a direct comparison. So I'm thinking this is probably going to diverge, because compared to 1 over n, I expect 1 over n to be smaller than this, because this is 1 over n, and then multiplied by a denominator, something going to 0 here in the denominator, should make my denominators get bigger and bigger and bigger here. Sorry, make my denominators get smaller, makes the whole fractions get bigger. So I'm suspecting this is going to diverge. So let's try, how about limit comparison? So let's do this first. So when I do this, what I'm going to do is my L equals limit n goes to infinity, 1 over n times square root n squared, square root n squared plus n minus n, and I'm going to compare that with 1 over n. And what I'm going to get here is these 1 over n sort of cancel. So I have 1 over square root n squared plus n minus n. So I'm going to use the same technique as before. I'm going to multiply top and bottom by square root n squared plus n plus n. Plus n minus n. I'm going to multiply by square root n squared plus n plus n. So I have difference, well, a minus b times a plus b on the bottom. So this gives me a limit as n goes to infinity. Square root n squared plus n. And on the bottom, I'm going to get n squared plus n minus n squared. So my n squareds cancel. And now I can divide top and bottom by n. Here, so limit as n goes to infinity. I'm going to get square root n squared plus n. Dividing by n is dividing by n squared inside the square root. Plus 1 over 1. And that's going to give me a limit as n goes to infinity. Let's see, this is going to give me a square root of 1 plus 1 over n squared plus 1 over 1. As n goes to infinity, 1 over n squared will go to 0. So this is going to be 1 plus 1 over 1. That's 2. So we had a limit of 2. That's a good result because 2 is between 0 and infinity. What that tells us here is that for big N, 1 over n times square root n squared plus n minus n is about twice 1 over n. So it was bigger, which is sort of what I was predicting, but not, a huge amount bigger, just twice that. So we got 2 here. So we have 0 less than L less than infinity, and n equals 1 to infinity, 1 over n. That series diverges. And because our L was between 0 and infinity, this series, n equals 1 to infinity, 1 over n, and the series we're concerned about, summation n equals 1 to infinity, 1 over n times square root n squared plus n minus n, either both converge or both diverge. Well, we know one of them diverges, so the other has to diverge as well. 1 over n times square root n squared plus n minus n diverges, except diverges. I think our series started at 2. Yeah, it started at 2 on the bottom here. So we'll start at 2. That doesn't actually affect convergence or divergence. Plug in 1. That doesn't even equal 0, so I'm not sure why it started at 2 instead of 1, but still same divergence. So that's really our answer here. This series diverges here. That was the limit. Can we do direct here? So let's just try a direct comparison. We suspect this diverges here. So let's try 1 over n times square root n squared plus n minus n. And we want to make this smaller here. So we know this is going to diverge. Let's see if we can make this smaller. How do I make this smaller? I make the denominator bigger. Well, and now sort of the obvious things run into trouble here. I could, to make the denominator bigger, I could drop this minus n, but then I'll get n times square root n squared is essentially n. I'll get a 1 over n squared, and that series will converge. So that doesn't work here. I think what I'd probably have to do is use that same conjugate trick, multiply top and bottom by n squared plus n, and say then this is square root n squared plus n over n times n squared plus n minus n squared. Have the n squareds cancel. This is square root n squared plus n over n squared. So that'll get me there. N times n gives me the n squared. And now I want to make this smaller. I can make my numerator smaller. I can do square root of n squared over n squared, which is n over n squared, which gives me 1 over n. So you have to do a little bit of work, but you can make a direct comparison work. And then we know that summation n equals 1 to infinity, 1 over n diverges. Harmonic series. So that tells us our series n equals 2 to infinity, 1 over n times square root n squared plus n minus n also diverges because it's bigger than something that goes to infinity. So you do direct comparison as well. There's sort of the same algebraic trick here. Maybe there's other things to do here as well. But last one. Okay, so we want to determine whether the following series converges or diverges. Here we have n over 2n plus 1 to the n. Now, I'm just going to say right now, this problem kind of screams to use a ratio test, which we don't really know about yet. I'll show you that at the end, how that would work out. Because it's something raised to the n, sorry, not ratio test, root test. Ratio test might work out as well, but it screams root test here. We don't know that. So what I'm going to do to analyze this is when I see n over 2n plus 1, to the n, what I think about is this is essentially, well, as n gets big, the 2n will dominate the 1. This is pretty much n over 2n to the n, which is pretty much 1/2 to the n. I have to be careful when I sort of get rid of some of the infinities and leave others. In this case, it's going to be okay, but this is all still just sort of a heuristic, like a rough guess kind of a thing. I'm going to go show it later. So this is just sort of telling me, do I think it converges, do I think it diverges? So I get 1/2 to the n. Well, what I know then is that I have a geometric series, it starts at 0, 1/2 to the n, that this converges, it's geometric here with the ratio r less than 1. So I suspect this should converge here, because what it looks like is I have 1/2 to the n. Okay, so let's try comparison. I'm going to do direct comparison. I don't really like doing the limits with the exponents here. A lot of times that gets a little bit ugly. It's doable, but these series, typically you do things kind of the easy way, and often they work out there if you figure out the right way to do it. So I'm going to do direct comparison. I'm going to just look at n times 2n plus 1 to the n. And because I think this is going to converge. Now, I don't know that yet, although I strongly suspect. I essentially have 1/2 to the n here. The only thing is that plus 1 is different here. If I didn't have the plus 1, it would be 1/2 to the n. So slight difference, but I suspect that really doesn't matter in terms of convergence or divergence. So because I think this converges, I have to show something's bigger. How do I make this bigger? Here, well, I can make the base, the n over 2n plus 1, bigger by making the n over 2n plus 1's denominator smaller. So if you think about this, this sort of is about here. It's actually, when I get rid of the plus 1, I'm actually making the denominator smaller, makes the n over 2n bigger, and because I'm raising this to a large power, here this should get bigger. Base is bigger, should get a bigger sort of exponent. That should work out here. So now we gotta, yeah, that should work out. Okay. And then what I get here is this is actually just straight up equal to 1/2 to the n. And then what I have is I have a summation n equals, let's see, 0 to infinity. I think we started at 0. Yep. 1/2 to the n converges. And, maybe it's nice to make a note here. Not terribly good at this. This is geometric with r equal to 1/2, which is less than 1 here. And so, because this converges, and we have that the series we're concerned about, the sequence inside is less than 1/2 to the n, that tells us that summation n equals 0 to infinity, n over 2n plus 1 to the n converges as well. So you can use a direct comparison test. It's not that bad. Here. Now, kind of promise this. Let's do a root test here. So when you do an n equals 0 to infinity, you may have seen this already or not, but when I see this to the n, there's another sort of test here, and that's like kind of a limit comparison. So we get an L. What we do is we take a limit as n goes to infinity of the nth root of this. So we do an. So we think of this as, well, really our inside, n over 2n plus 1 to the n. And then in the root test, so this is called a root test, we'll talk about this more later, you raise whatever's inside the series to the 1 over n. Now when you do that, you have to the n times 1 over n. Those multiply. That just gives us limit n goes to infinity, n over 2n plus 1 here, and that's going to be 1/2. Now the reason I thought do root test here is I know when I raise to the 1 over n, that exponent of n is basically going to get canceled out. So that exponent actually makes this root test probably even simpler here. It sort of just screams, hey, do the root test. Now, we don't know if this converges or diverges, but the root test says that if you do L equals limit n goes to infinity, you do like an, that's the n over 2n plus 1 to the n, to the 1 over n. And what we get here is that if L is really 0 less than equal to L less than 1 here, then sum n equals, say, 1 to infinity an converges here. If L is greater than 1, sum n equals 1 to infinity an diverges. If L equals 1, our test is inconclusive here. Now, we got 1/2, which is less than 1. So we get really that our original series converges here. I need to probably fill in the AN for this original series here. This is a quick intro to the root test. Works out pretty well here. The general idea here is that essentially if you take an nth root and you get a constant less than 1, that this series is essentially like a geometric series where it's whatever L is to the n. So if L is less than n, this converges. If L is less than 1, this converges. If L is bigger than 1, it'll diverge. At 1, things are a little funny, and you can either converge or diverge here. Typically, that means the root test wasn't the right thing to do.